So I know that we've done a whole lot of different kinds of nomenclature to the point where it looks like every kind of compound or every week we had a different kind of nomenclature, and it was trying to keep track of all those different things. Hydrate nomenclature is going to be it's going to feel kind of familiar. It's going to be an add-on piece to things that we've already done. So we want to start with things that we've already done, this isn't going to be a full-on review, but we want to make sure that all that previous nomenclature that we've done, that we hang on to that. So if it's an ionic compound, we name it as an ionic compound. If it's a non-metal, we know what to do with that. If it has the ic and the us endings as a possibility, like ferrous, ferric, we know how to do that stuff. If it's polyatomic ions, we recognize the polyatomic ions and we can work with those. So the one thing that comes up sometimes with that, and this is probably the example where it happens most often, is SO3. When we first learned it, was sulfur trioxide. It was a non-metal compound. We have something on the polyatomic ion list that looks a little bit like it, but there's a couple of key differences. Number one, SO3 as it stands, no ionic charge, plus I'm not going to give you half of a compound, so you're going to have a full compound. If it's an ionic compound, it will be a positive ion with a negative ion. This doesn't have either of those. It doesn't have a metal to go along with it, and there's no ionic charge, so it's going to be called sulfur trioxide, as it has been since we started doing nomenclature. Keeping in mind also that you're going to have a polyatomic ion sheet available to you for the rest of the course. At this point, though, we should be moving away from needing the names on the periodic table and also the ic and the us ending names as well. However, that's kind of a story for another day, and same thing with the charges. You should be able to do a lot of the stuff without being given those charges. Okay, let's talk about hydrates then. First of all, what is a hydrate? Now understand that in order to do the nomenclature of a hydrate, we don't really need to understand that much about the chemistry of a hydrate, but just so we have a bit of a broader context for this, is a substance that contains water. Now for us, particularly when we're talking about nomenclature, it's going to have water. I don't like the word trapped, but that's maybe one of the better words that we can use, stuck inside the crystal structure, trapped inside the crystal structure. It's not that it's there against its will or anything else like that. The water typically moves in there all by itself. And it's also often in some sort of measurable or predictable ratio. In other words, I can know that this crystal structure has X amount of water, and that's kind of the job with nomenclature of hydrates, is identifying how much water is in the crystal structure with each molecule or each particle of the compound. In terms of the terminology, if the water is there, we call it a hydrate. If the water is not there, we will identify it as being anhydrous. Now, in the case of the cobalt-2 chloride or cobaltous chloride, the hydrate and the anhydrous form are quite recognizable from each other. The anhydrous version has this nice blue color, and the hydrated version, where there's 6 molecules of water associated with every particle of cobalt-2 chloride, has a much darker red, almost a purplish color to it. So they're quite a different thing, so they visually look different. So how come we've never heard about hydrates before? Well, the main reason why we haven't heard about them before is that they are chemically identical to the anhydrous version. So an anhydrous cobalt-2 chloride has exactly the same behaviors, exactly the same chemical properties as the hydrated cobalt-2 chloride. But the water does add mass. Now, other related but, well, let's say slightly irrelevant to our conversation right now, is that oftentimes if you're using a chemical and you weren't really sure, you would heat it up to drive the water off so that you knew you were only using the anhydrous form. So that's another reason why we don't usually talk about the hydrate, is we often won't use them if we're trying to do proper chemistry. So going back to that thing about the mass, and again, these numbers themselves aren't really important, but if you look at the cobalt-2 chloride again, when I have the hydrated form, the molar mass of that compound with the water included is significantly different than the molar mass of the anhydrous. So if you were massing out 5 grams of that stuff, it's actually very, very important whether or not you are using the anhydrous or the hydrated version, because the number of moles of compound, cobalt-2 chloride, will be quite different depending on whether you're using the anhydrous, no water, or the hydrate with water. However, our job is to do the nomenclature today, so let's look at that. If you start with a chemical formula, the chemical formula is going to take this kind of form. You'll have the ionic compound, as you've seen ionic compounds for quite a long time now, with a dot followed by a number and H2O. So the water is not chemically bonded in there. It's not really part of the formula. It's attached on at the end, and we use that dot to suggest that the water is associated with but not bonded to the compound. So then the job becomes, I have to identify the number and the water and the ionic compound. Well, all previous nomenclature stays the same, so I'm going to keep the ionic compound name the same thing. I'm not going to change how I do that. So now hydrate nomenclature becomes ionic nomenclature with an add-on. Include that water. So I'm going to use a prefix to represent the number of waters, and it's the same prefix as we've been using before. Mono, di, tri, tetra, penta, so on. And then what I'm going to do is I'm going to identify the water using the word hydrate. Okay, so putting all of that together, if I had this copper 2 chloride with 6 molecules of water associated with it, it's going to be copper 2 chloride, no surprise, hexa for 6, hydrate for water. And that's it. That's all there is to it. All I'm doing is adding on the water piece. So in this case, CuSO4, well, that's copper. SO4 is sulfate. Sulfate has a -2 charge, which going back means copper is going to have a +2 charge. So I could call that cupric sulfate or copper Roman numeral 2, either way. Copper 2 sulfate, cupric sulfate, and then 5 water. 5 penta, hydrate, water, pentate, hydrate. So copper 2 sulfate pentahydrate or cupric sulfate pentahydrate. Okay, and you can look at the next one as well with 7H2O. 7 is hepta, so it'll be a heptahydrate. Too easy. If I'm going from the name to the formula, well, obviously my name is going to include the name of the ionic compound, and it's going to include a prefix with the word hydrate, which means I know what to do and what that means. I'm going to do the nomenclature as I've always done and then add on that water piece. Now, the water I separate from the formula with a dot. So all I have to do really is remember to put in the dot. Okay, this prefix tells me how many waters to include, and the word hydrate tells me that it's going to be water. So same prefix as before, mono, di, tri, tetra, penta, so hexa, and so on. Calcium chloride dihydrate, calcium chloride, ionic compound, total positive charge equals total negative charge. Dihydrate means 2H2O. Ferric bromite tetrahydrate, well, ferric means the higher of the two charges, that's +3 for in case of iron. Bromite is one of our polyatomic ions. Tetra means 4, hydrate means water. So nomenclature as normal, add on the water. And that really wraps it up. Hydrate nomenclature is really no different than anything else we've done. It just includes an extra piece. So our names get a little bit longer, but not too bad. Okay, so you should be able to do hydrate nomenclature at this point, and we'll talk to you another time.